All right, guys, I hope you had a good weekend, and hopefully on Thursday the notes went okay that you guys are working on and the homework that you were working on about absolute convergence and conditional convergence. So right now is a warm-up that talks about alternating series and convergence and if it's absolute or not absolute, if it's absolute or conditional. So try this out, hit pause, try this out. On the next page, I'm going to go over the answers that I produced. So for right now, hit pause, good luck, and then when you're ready to go over it, you can hit play again. Hit and pause. All right, so for the first one, it says approximating the error. Luckily, this is an alternating series, and as long as it's an alternating series, the error comes from the next term. So alternating series, error comes from the next guy, which is the n+1 term. So when I look at that, you don't need to worry about the alternating part anymore. You just need to worry about the core part to it, not the sign change. So I'm looking at when is 1 over n+1 less than the error that I want, which is 0.23. When you cross multiply and solve some algebra style, you're getting n has to be greater than 3.34. So you need 4 terms. To make sure your error is less than 0.23. You love doing error questions with the alternating series. Just a little reminder, you did not necessarily like the Lagrange error bound. That came from the last test, and that one had a little bit more detail to it because you had to talk about the n+1 term, but that meant you had to build the n+1 derivative and maximize that, if you guys kind of remember that. Here, you just look at the next term. That's why AP uses this type of question a lot. Okay, this one, we have to talk about what's this series going to do, okay? Right away, it's an alternating series. The degree on bottom is bigger than the degree on top, so it's going to go to 0. And since the sequence goes to 0 and it alternates, it is definitely convergent. That just means the series is convergent. I have not put the series in the absolute value part yet, so I haven't put the guy in jail yet to determine if it's an absolute convergence or just a conditional convergence. So that's what we're going to dive into here. So I'm looking at the absolute convergence of the sequence, or the series, sorry. So I'm looking at n squared over n cubed plus 1. Notice I took away the absolute, the alternating series part. That to me, that red piece to me looks like n squared over n cubed, which is 1 over n. So from Tuesday's notes, I am going to use a limit comparison test. Okay, I'm going to look at 1 over n. And just, you can do either the limit comparison test or the direct comparison test. Okay. So let's look into this. Look over here at the right, just for a little reminder for you guys. The limit comparison test versus the direct comparison test. You do the direct comparison test. This black picture over here on the right is talking about if I have a divergence series and below it I have a guy, what does that mean? Can it be convergent or can it be divergent? Do you know yet? This is on the black one. Okay, from the direct comparison test, you don't know what you have here. Okay, just a reminder on that picture. And let's look at this picture. If you have a divergence series below, what do you know if you have something above it? That for sure diverges. Okay? So if I was going to attempt the direct comparison test, do we all agree that immediately this guy is divergent? Okay? By the P series, P is 1, it's divergent. It's the harmonic series. And now let's look here. What happens when I take away the plus 1? Does that make the bottom bigger or smaller versus this bottom? It makes the bottom smaller which makes this, is that correct? I made the bottom smaller on the right side. So if it's smaller on the right side, then I'm dividing by a smaller number, which means the thing's bigger. Okay? So here's the issue. Is this, using direct comparison test, is this the black one or the blue one? We have the divergent, so we definitely have the divergence. So it's either here is the divergent, here's the divergent. But we care about this piece. And that piece is less than it. That means that piece is here. So I don't know what I have. So the direct comparison test doesn't help me. Okay, because so the direct comparison test does not help me. Because now I'm stuck here where I capped it with a divergent test, the 1 over n, and I have something below it, and I don't know what that's worth then, if it is convergent or divergent. So instead of the direct comparison test, and I think I've mentioned this a week ago, a lot of times it's nice just to go directly to the limit comparison test, and then you don't have to worry about, hey, which picture did I use here? Is it conclusive or not? The limit comparison test just says, take the limit of one guy over the other guy, and if it's a finite number, boom, they both do something together. So let's take a look at it in the limit comparison test style. So I'm going to compare the limit of the original guy over 1 over n. So when you divide fractions, you flip and multiply. So it's really down to the limit as n goes to infinity of n cubed over n cubed plus 1. And that goes to 1, which is a finite positive number. So you know both converge or both diverge. And since this guy diverged, we've already mentioned that, then we know the other guy also diverges. So in summary of what you've done, that guy is conditionally convergent because the guy by himself converges by the alternating series, but when you put it into absolute values, then you look at the limit comparison and that guy diverges. So therefore, the whole series is conditionally convergent. It only converges if you don't have the absolute value with it. Okay? So I was just kind of a warm-up problem after the weekend. And hopefully you realize you got to know these tests because I've just talked about all on this page. Alternating series, direct comparison and why it didn't work. It was inconclusive. Limit comparison, p-series, and then absolute convergence and conditional convergence. So a lot of tests that you have to kind of know. Which means, why not? Let's learn 2 more tests. Okay, the ratio and root test. Okay, today I'm doing both of them. The ratio one you're going to see a lot on AP. It is probably the most important one on the AP test. They ask it a lot. The root test is rarely tested on AP, but I still want to teach it because it's ridiculously easy to spot and it's ridiculously easy to do. Okay. We'll spend more time today on the ratio test though, since it is the main one. And here's what the ratio test says. If you have a series with non-zero terms, okay, key thing, non-zero terms, then it will converge absolutely if the limit as n goes to infinity of the next guy over the current guy, all in absolute values, is less than 1. So if that ratio, hence the test, if that ratio is less than 1, it converges absolutely. Likewise, if that ratio is greater than 1, and it's silly, it's funny why they put that. If it's greater than 1 or if it's infinity, well, that's the same thing. Okay, so if you're finite and greater than 1, or if you're infinity, which is obviously greater than 1, then the thing diverges. And notice, the thing diverges. That means everything diverges. Okay? And then if it equals 1, you're stuck. And then you got to go back into your toolbox and use a different tool. Okay? So that's the ratio test. Let's look at an example of it here. Okay? Using the ratio test. Okay, determine the convergence or divergence of that thing. Okay? And I'm telling you right now, let's use the ratio test. So let's try this out. So the key thing to the ratio test is I'm going to do the limit as n goes to infinity of the next guy over the current guy. So let's see, this is the limit, n goes to infinity. Here comes a big ratio here, 2n plus 1 over n plus 1 factorial, all over 2 to the n factorial. At first glance, you're like, whoa, that's a lot of algebra going on here on a big-time fraction. Okay. What's nice, though, is things will simplify pretty quickly. Okay, first thing, fraction over fraction, I am going to flip and multiply. Flipping. And then we are going to simplify this. So let's see what we got here. On this part, I have 2 to the n plus 1 on top and a 2 to the n on bottom. Lots of 2's cancel there. The top guy has one extra 2 to it, so he is a 2 on top. Now here, with factorials, a lot of these things cancel out, because you need to remember, what does n plus 1 factorial mean? Let's look at it with numbers first. If I did like 9 factorial, is that the same as 9 times 8 factorial? Okay? Or if you wanted, you could have done something like 9 times 8 times 7 factorial. Okay? Likewise, n plus 1 factorial would be the same as n plus 1 times n factorial. Okay, you list the first guy and then you factorial the rest. And so because of that, the n plus 1 factorial on bottom is just 1 bigger than the n factorial on top. So the thing that's left over is that n plus 1. Now, when you look at that limit, that thing goes to 0, which is less than 1. So that means my series is absolute convergent by ratio test. Okay? That's just one of them. I'm going to give you a couple more examples where it works, where it doesn't work, and then when you know you should use ratio tests. I'll show that in a second. Okay, so we're going to try them again on A and B. Okay. Notice again that there are, on these problems, there's factorials on some of them, and there's numbers to exponents, or n to an exponent. So you're going to see a lot of that with the ratio test. Let's look at A. Limit n goes to infinity of a n plus 1, next guy over current guy. Okay, let's see. N plus 1 squared, 2 to the n plus 1 plus 1, all over 3 to the n plus 1, all over n squared 2 to the n plus 1, all over 3 to the n. Now, I'm writing it like this currently, but realize you could write it right away this way, the way I'm about to. You already know it's going to be a fraction over a fraction. So if you want, you could just write immediately the part where you already flip it. There's the next guy. And if you already know you're going to divide by the current guy, you could also just divide or flip and multiply directly by that current guy. So I'm writing that right there. Oh, that's the absolute value part. Okay, so let's take a look at this. It looks like there's a lot of things here. I'm going to try and color coordinate for you what can cancel out. I'm going to look at this chunk. 2 to the n plus 2, 2 to the n plus 1. There's more 2's on top, and there's only one extra 2 on top. So there's a 2 on top. Okay, let's look at this piece. There's one extra 3, but he's on bottom this time. So I put the 3 there. Now, do not get giddy and just start canceling things out on this n plus 1 squared and n squared. They are different beasts. Yeah, they're both squared, but it is one guy squared versus another guy squared. They don't cancel out immediately. So I'm going to put n plus 1 squared and n squared there. Okay, that's it. I can't cancel just from that. But from here, you should be able to say, okay, let's look here. The degree on top is 2, because it's n squared. And the degree on bottom is also n squared, so they are the same. And since I'm going to infinity, you just look at the numbers in front. So that goes to 2/3, which is less than 1. So series is absolute convergent. So it converges, and the absolute part of it converges. Okay, so that was A. Now let's look at B. And send B down to here, and we'll scroll down to it. Okay, this is n to the n over n factorial. Okay, so limit n goes to infinity of n to the n, so that would be n plus 1 to the n plus 1 all over, what was this problem again? N factorial. N factorial. So that's n plus 1 factorial. And again, for the notes, I'll just write it this way for a second. Okay. So now I am going to flip and multiply. Okay, so I flipped and multiplied. So now let's take a look at what we got here. I'm going to deal with this part first. Just from the previous example, you know that that is an n plus 1 left over on bottom. Okay. And here, let's see, here. This stuff right now, nothing cancels. Okay, so I'm going to leave that currently as this. Now, watch how I manipulate this a little bit. This is going to be n plus 1 to the n all over n plus 1 n to the n. Now, all I've done so far, the bottoms are the same. Look what I did with this piece and how I broke it up into one of them and n of them. Okay? One of them and n of them. The reason I did that is because now I can look and say, hey, that part cancels. So now let's see, I'm looking at n goes to infinity of n plus 1 to the n all over n to the n, which is limit n goes to infinity of n plus 1 over n to the n. Okay? Which, let me rewrite it one other way for you guys, and it might look familiar to you. 1 plus 1 over n to the n. Now, we've done this problem before. We have done it with L'Hopital, because currently if you look at this, when I plug this in, I get 1 to the infinity, which is indeterminate. which means we should do L'Hopital. But this is a famous one, and I want you to start remembering this one and going, this is so famous, it becomes a letter of the alphabet. So you're like, what? A letter of the alphabet? Pi is not a letter of the English alphabet, but E is, that goes to E. What you would have had to do if you did Hopital is you would have taken the natural log, then you could have done the Hopital, natural log part, then you would have done Hopital, then you would have E'd it back, and your answer would have been E in the end. You can look at notes or whatnot, but it would have been E. E is greater than 1, so the whole series diverges. Biratio test. Okay? So, here's the end of video 1.